Um, we have 7 students here. Who else not here? Where is Vina? Okay. Okay, Vina is here. All right. Okay, you can continue. All right, so if you look at your question 20, it asks you to study and observe the relationship between parameters. So on this chart, on the left-hand side, left-hand axis, you have CDF represent drag coefficient. And then the horizontal, you have Reynolds number.
Sir, cannot see the slide, only see your face.
Oh, sorry. Yeah, sorry. Should share. Okay, now you should be able to see my screen.
Yes.
All right. Now we are at question 20. Question 20. We have CDF on the left. CDF means drag coefficient. And then horizontal, you have the Reynolds number. L means it refer to a certain length or characteristic length. So what is important you look here is that what happens if you increase the Reynolds number. And Reynolds number, you know that it link up with the speed, the speed. So if you increase the speed, so you can see here 10 power 5, 10 power 6, 10 7, 7 and all this. So if this one you increase the speed, what happened to the CD on the flat plate? You see the flat plate here? The flat plate parallel to the upstream. Now, yeah, so on a flat plate, if you increase the velocity and you're having a laminar flow, your CD, your drag will drop. The drag on a flat surface will drop. Again, so for those doing the assignment that deal up with the flying object, then this one is important. All right. And then you have a transitional phase, and then it comes to turbulent. So this is a turbulent line. So of course, in the turbulent also, if you increase the speed above the surface, you see the CD value also decreasing, right? Also decreasing. And on the right-hand axis here is the relative surface roughness, E divided by L. And this one is a bit different from the Moody diagram. This is roughness divided by L. Moody chart is E, the roughness divided by D. So this is L. So if you see the roughness ratio, if you view from the bottom, from the top to bottom, so the ratio is increasing. The numbers is increasing. No, it's decreasing because more and more zero. So 10 power negative 3 increase to negative 6. So the ratio is decreasing, meaning how you get a smaller and smaller value if you look at this equation is that the length is getting longer and longer. This component is getting bigger and bigger so that your number is decreasing. So it meaning that each line, if a certain line, it means that the length is increasing. Assume that the roughness constant. So the length is increasing. So if you increase the length, the drag will also drop a stage to another stage, for example. Okay. And the line was almost constant in a very high speed region. Okay. And then for the table on the right here, you will see that there is an equation used to build all this line. For example, the first line, laminar line, this one, CDF equal to 1.328 divided by Reynolds number L 0.5. This is for this line. Now you can use this equation to discuss about the assignment, right? So all this will give you the drag coefficient, and then drag coefficient you can calculate the drag and lift. Okay, and traditional, this one is for this line, and turbulence smooth plate, this one, this line, turbulence smooth plate. So you can also discuss what happens if the surface of your aircraft, paper aircraft, is smooth plane. What happened? How to add the smooth surface? What material that you propose to use, for example. Okay. So, and then this one, completely turbulent, is all this, right? This region. So actually it's a dot line, the dot line, this one, right? So, okay, this is the effect. If you increase the Reynolds number, what happened to the CD? What is the relationship between CD and Reynolds number? Okay. Let's look at one example on application. This is tutorial number 21. So you're given a water ski here on top of the surface, water surface, and the velocity is from the left to right. The velocity from the left to right, or you can say that the object is moving towards the left, right? There are two ways you discuss about motion. One is the object stationary, and then the reference object moving. So it depends on the perspective. And then you have 2 points here, point 1 and point 2. You have x equal to 0 as point 1. And then there's a certain, the second point at the edge of the water ski board, x here, right? So the length is 4 meters here. And then the width given is 0.5 meters. Okay, moving through a 21-degree water with a velocity u. Okay, and every time you see there's a temperature there, then you refer to a table. Right? Refer to a table. Estimate the drag caused by the shear stress at the bottom of the ski for velocity between the velocity range 0 to 30 meters per second. So we want to estimate this drag. So what are the strategy we use? Okay. Okay, I'll come back the answer for this one. I think I accidentally removed some of the things. So we will come back to question 21 later on for the answer for the drag caused by the shear stress later on. Okay, let's look at question 22. So we start to look at friction drag. Friction drag given by capital D with a small f. It represents a drag caused by friction. All right, and friction always deal with shear stress. This one, deal with shear stress. Shear stress. Given by this equation. If you want to calculate the friction drag because of the shear stress, given by half rho u square times the BLCD, which is in the same structure of the drag equation, D equal to half rho V square CD A. Okay. So again, this one is dynamic pressure. B times L get the area. For example, you have a plate, right? This is the area. Okay, B times L get the area. CD is the lift is a drag coefficient, right? F. So we have seen this graph before just now, the CDF graph in your hands out question 20. And yeah, this is the equation that we're looking for, the friction drag. So for question 23 is a bit lengthy process. Later you can come back. So you just focus on the screen. It's a bit lengthy step, but try to understand the strategy. So you're given a cylindrical cylinder. It is you have a cylindrical pipe or cylindrical object, solid pipe. Then there's a flow across this body. So according to a more advanced theory boundary layer flow, the boundary layer remain attached to the cylinder up to the separation location, which is here, about here. So at 108 degree. So if you measure from experiment, your force measured by experiment, left hand side is a F. F theta means the force from equation given here. If you measure from each of the angle here, for example, degree 0, 20, 40, and then up to here, maybe 108, maybe about here. 108.8 degree. There is no more force. All right, up to here, if you put a sensor here, there's no more force measure here. So you measure 0 at this location. So this is the experimental graph collected from experiment. So given by this equation, force created on the surface equal to mu, shear stress, square root of Reynolds number divided by the dynamic pressure, half rho u square. So on the left hand side is force, and then you look at the graph here. It means that if you measure from 0 degree up to 120, this is the data that you collect from the experiment. And how you identify separation on the object means there is no force that you can measure. So if you look at any graph, that at any point on the object, if you see there's a straight line or there's a 0 force created on the surface, it means the separation happened. Okay. So they asked us to determine the drag coefficient, right? Now, how does it happen? So these are the keywords. Then we copy the diagram given here. So the diagram, this is a free body diagram. So we have a Reynolds number, Re equal to rho Vd divided by mu, because this is a cylindrical body. And we measure, if you look at very, very small particular area here, we zoom out, we get this diagram. So we have a small area here, the A. How we calculate the A that we use is d divided by 2 d theta. So this one, if you study calculus, you have a very small area and you want to find the circumference here, very small area with the r, then you link up. There's an equation you can link S equal to r theta. Okay, S equal circumference here equal to r theta if you have a very, very small area angle here. So You can revisit this concept in the advanced mathematics or in calculus. So this one, and radius and theta here is radian, in radian. Okay, so these are the concepts. So we always look at a force rather than the shear stress and the pressure. So we convert, when we study the lift and drag, we only look at two components acting on the surface, which is the pressure and shear stress. So, and on this diagram here, you will see the action of the shear stress. If you take the shear stress times the area, you get shear force. You take the pressure times the area, you get pressure force. Okay, pressure force, and there's an angle there. There's an angle. Okay, so we'll use the drag equation. So the first equation we use is drag equation. Again, you don't need to copy. Later you can get my slides. Just try to understand how we solve this question. So we pull out the drag equation given by integration of all the force in x direction, because we already define, we refer to our upstream velocity, all the direction, all the force parallel to the u, we call it drag. All the forces perpendicular to your upstream, we call it lift. So in this question, it asks you to find drag coefficient. So we only focus on drag. Okay. If the question asks you to find lift coefficient, then you use the lift equation. So for this question, we focus on drag. So drag equation given by integration of P cos theta dA plus the shear stress component sine theta dA. So this one covered in the previous slides. All right. Then we cancel out. We cancel out for the first one because for the drag in this with the pressure component, because pressure always perpendicular to the surface. All right. So our angle for our pressure component we can take out. Okay, we can take out. We only have shear stress. Okay. So for the friction drag is directly to the shear stress. We are looking at friction drag now because the question asks you to find for CDF, drag coefficient, friction drag coefficient. So we're looking at the shear stress here. So our equation reduced to this equation. All right. So this equation we carry again. I enlarge the diagram. So I explained about the relationship between the circumference, the radius, and the theta just now. So you transform the equation that we have just now. So shear theta dA, we change our dA because we integrate using the angle here. And the angle here is in radian, 0 radian and pi radian. Pi, in one circle, we have 2 pi radian. So we are only looking at up to 180 degree because another half is symmetrical. So we look at only up to pi angle or pi radian. And then we change our dA into d divided by 2 d theta. I already explained how to find this equation just now by using the relationship of your circumference, radius, and theta just now. So you convert dA into this term, pull out all the constant in the equation. Where is constant? B constant, the diameter constant, 2 is constant. So sorry, just now I missed out the 2. It means that we calculate the overall cylindrical subject. All right. For this one, this term only, we only calculate the first half from here up to here. Then the other half is the same. So we times 2 here. Times 2 this term. Okay. So we get this equation. B is the length of the cylindrical. cylinder. And the radian, again, the angle here is radian, not degree. Recall drag equation, D equal to dynamic pressure times CD times A, so you rearrange to get the drag coefficient structure. You transform this equation, general equation, into the specific friction drag coefficient. The other still the same, only you change the A, because here we have the B plus the D, we get the A. You take the B times the D, you get the A. How we get the, why we get BD here? Because if you have a solid cylinder, you have a flow from the left to right, what will will the wind or the velocity see from on here? You are seeing from the front, you are seeing a cross-section area. What is the length here? Is actually the D, and B is the length. So this form your A here. Right, this form your A. So that's why we can write our A as a BD. Again, if you focus on friction, it's more on what is being seen and being touched by the velocity, contact surface by the velocity. Okay. And then we put in the equation just now, because we have our dF equation we derive from the drag equation just now. We substitute this one inside here, right? dF tau sine theta d theta. We cancel out the B and D because we have BD here, become this one. All right, this is what we obtain. So we are given this diagram. We want to put our equation. We want to put this CDF 1 over half rho u square integrate of your sine of your shear stress sine theta in this term, in the F theta term. So we rewrite our equation. All right, if you put your rearrange this this equation, you substitute inside here. Let me see here. So I start to develop the equation. So the first step is that I create something out of nothing, meaning I start input hi-hat of square root of Reynolds number both sides, because we want to change, modify our equation here, look like this one. So we need to balance the equation. So we input the square root of Reynolds number in the equation, so that later on at the end we will see this form. All right, we will see this form. All right. So once you created this one, then you pull the half rho u square into the equation. You pull this term inside there, then you get this term. All right. Because you pull your half rho u square into the right hand side of the equation, the combination become F theta. Integration of from 0 to pi, you get a CDF equation. So again, this one is you plot using Excel. Or you can use the Excel, or you can use the online graph plotter. Key in the data to plot this kind of chart, to calculate the value. What happened if it's 0 radian? What happened to your F sine theta, right? So you find the relationship between these two. Right? This graph is integration of f theta sine theta d theta, because you integrate f theta sine theta towards theta, right? So this integration gives you the area under the graph, area under this graph. Right? This whole thing is area under the graph. So to calculate the area under the graph, you can use software to solve it. Right? You can use trapezium approach. You can use 1/3 sinusoidal method, right, under the graph, right? So by software, you're able to find area under the graph is 5.93. So at the end, you can conclude that CDF equal to 5.93 divided by square root of Reynolds number. Okay. So the strategy of question 23 actually is an exact scenario that we will come across when you conduct experiment to find the drag coefficient of a rounded object. So if you go conduct this experiment in the wind tunnel, then you can collect the forces or pressure on each of the point. You have a cylinder body, then you you drill a hole on the body. You drill a hole, and then you plug in all the tube, right, to a pressure gauge. So for example, 0.1, 0.2, 0.3, 0.4. So 1, 2, 3, 4. I mean, this is the pressure gauge with a mercury inside. So you can see the pressure created by, for example, this one. You see the pressure P1, P2, and then you convert into force later on, then you plot this kind of graph. So when you plot this kind of graph, you can refer to a standard testing standard given by this equation. Then you convert what you get from the experiment and then find the lift coefficient. All right. So you start with the drag equation given by pressure and shear stress component. However, for the friction drag only link up with the shear stress, so we don't link up. So the pressure component don't have any significant effect on the friction drag. So we cancel out the first one. All right. So our equation reduced to this form. Then we further redevelop our equation in the term of shear stress by changing the dA into the dimension that we have in the experiment, which is the B and the D, the width and the diameter of the pipe or cylindrical body. Then you use the conversion of the definition for the drag coefficient, right? Then you compare the result with the graph that we plot from the experiment. All right, we equal the two equations. This is generated by ourselves because we want to redevelop our equation, this one in the form of force that we can measure from the experiment. Okay, once you develop, then you can transform your equation in the experiment term. This is all the data we collect from experiment in the force magnitude, force data. Then software to calculate graph, area under the graph by having, because it's the integration of F component and the degree component. Again, the unit is radian. All this you can done using software to calculate area under the graph. So this one is area under the graph. Okay, right. So you put inside there, and then you get the CDF for the experiment. Okay. Right. Now maybe for your coming final exam, we will just give you, because it's an open-ended question or it's an online question. So again, we will give you a realistic wind tunnel results, and then you try to solve for the CDF. All right. Of course, all these area will be given to you. We will calculate for you. Only we want to see whether you know how to tap in the information or not. Right, we will give you, for example, a few chart. First chart we will give you this one, force degree versus degree in degree, and then we will you need to convert into pi. This chart. You'll see another chart given with this force versus radian, and then we'll give you the area for graph under B. Then we'll see your intelligence, whether you know how to link this graph in the equation derived. So this component is the area under the graph, which is a bonus mark straight away you plug in from the question. Straight away you write given area under the graph is so and so, and you conclude that the CDF equal to 5.93 divided by Reynolds number, square root Reynolds number, and then you might further ask you to calculate the drag force, friction drag force on the surface. So you use this equation to calculate the drag on the surface. This one, yeah, you use drag. This one, because you already calculate this component already. The question might further ask you what is friction drag on the surface. So you just rewrite this equation. BD times the CDF. Because CDF is given just now, so you have a number and a square root of Reynolds number. You are given the speed of the wind tunnel, for example, 30 meters per second. You know how to calculate the Reynolds number, all right? So you calculate the Reynolds number, substitute. You have the rho, you have the V, you have the B, you have the D. You're able to find friction drag force in Newton. Okay, so they give you hints. Just get prepared. Okay. Yeah, any question on question 23? Any question? Any part that you don't understand? Any part that you feel very weird, you don't understand? Any part that you don't understand? Okay, go and think. What happened if I change the shape of the body? I change it to prisma. And then I have pressure. Pressure 1, pressure 2, pressure 3, pressure 4, pressure 5. Up to here, maybe 90 degree. Then you get a graph. You have a pressure graph versus angle. This is the theta. Then you get a certain very weird graph. All right. P versus theta, or you given force theta, similar. So the area here, you change the dA here will be different. Huh? dA here will be different. Here is your there's an equation to find the, because you're seeing from here, maybe you give it the L, so your dA will be L times the B in this case, right? And then the rest is still the same. The question will ask you calculate the friction drag acting on the front portion of the prisma. Yeah. So are you able to find? Okay, the steps still the same, only change the A to a term, and then yeah, just convert accordingly to the graph. You put the hard part is, the challenging part is this one. I think most of you will miss out this part. This one. How to convert this equation to this equation by referring to the graph left-hand side component. So this equation was given. So do you know how to convert the developed equation to a new equation by matching up the parameter given? So in this one, there's a skill set here that we expect you to know, is that we'll expect you to cleverly modify the equation, match with the experimental data. So in this case, we change the equation, this one, in terms of f theta by recreating the square root of Reynolds number front and back, and then we push this one inside the equation. We get from this one to this one. Okay, then maybe in the exam, I will just give you the final results conversion. I give you the area under the graph, this one. Of course, I won't write out this one. I'll give you area under the graph. Area under the graph of f theta versus theta radian is 8.18 unit square. Okay, calculate the CDF. So you convert this equation into CDF. From CDF, calculate dF equal to what in Newton. Okay, any question? I'll give you hints already, yeah? So I hope you're able to stop. Any question? All right, if no question, I think we have a short break. Just now we come back forward. Okay, forward, yeah. Okay, let me see then. Okay, we'll go for a few more slides, then we stop for a short break. We continue with question 24. Just now we cover the friction drag. Now we look at pressure drag. Just now we finished friction drag. Now we continue with the pressure drag. Given by dP, this is due to the pressure. So when you answer question, be careful to look for the exact instruction. So sometimes we ask you to find friction drag. Sometimes we ask you to find pressure drag. So be careful. And if it's a pressure drag, then sometimes we use the word of form drag. It's also referred as a form drag because it's linked up with the geometry. So you link up with the geometry. Okay. So I mentioned the word geometry, it will link up something with the assignment. All right. So you need to mention about pressure drag also. All right. So again, this is a small diagram that you see under question 24. You will see a small area, dA, and the action of pressure on this surface. All right. So P times dA, you get the pressure force acting on this small area, dA. Right. Yeah. The rest you can read yourself. So only you need to be careful is that the pressure drag is in the function of magnitude and orientation of the surface. Pressure drag is defined in the magnitude of pressure, P, and the orientation of the surface, which is theta. Theta means the reference axis to the area here. You have a theta. So theta tell you the orientation of the surface. Okay, so this is answer for your handout question 24. Then we look at a graph. A graph. Look at the graph. So there's a few more equations. So pressure drag, again, we write in the integration of pressure cos theta dA by refer to this diagram. Because if you break the magnitude of the diagram, so the blue arrow is the resultant pressure. It is the absolute pressure magnitude or pressure force. This is the pressure force because you already convert your pressure into force. So we call this magnitude as a pressure force. You can break the pressure force in vertical and horizontal. And we know that we are focusing on drag. We are focusing on drag. Again, drag is parallel to the upstream. So this is the pressure drag component. This is the lift component. Okay, and again, in this case, we don't focus on the vertical component because vertical and perpendicular magnitude vector to the upstream is giving you the lift. So you're focusing on the drag. So you convert this magnitude to this magnitude, you get cos theta times dA. So you can use this one to write the lift, the pressure drag coefficient. So pressure drag coefficient given by, you just rewrite the equation for drag again from the general. Drag equal to half rho v square drag coefficient times the area. Rewrite this drag equation in the coefficient form, give you by drag force divided by dynamic pressure component times the area. dP, which is our pressure drag, given by the equation of this one, because this is the orientation of our object, because just now we already defined pressure drag was given in two things or two items. One is the magnitude of the pressure, one is the orientation of the surface. So we need to rewrite our dP in the integration of pressure magnitude, and the orientation of our surface. All right, and then we further reduce to our equation because we know that our P divided by P is your pressure. P divided by half rho U square, you will get Cp, right? Cp cos theta dA divided by A. So your Cp here in this equation, Cp equal to P minus P0 divided by your dynamic pressure. So you need to copy this equation somewhere under question 24 to remind you the pressure coefficient given by Cp equal to P minus P0 divided by dynamic pressure. P is the reference pressure. Okay, reference pressure. All right. Now, just a pop quiz to test your understanding is that does the level of reference pressure influence the drag directly, and why? Does the level of reference pressure influence the drag directly? Why? So this one also will you need to explain in your assignment, all right? Because of the thing. So the level of reference pressure, it do not influence the drag directly, because net pressure force on the body is 0 if the pressure is constant on the entire surface. Yeah, the answer is no, because the net force, the net pressure force on the body is 0, because all the body exposed to the reference body. Because if you have a body, you want to find pressure drag on the body, because this body exposed to atmospheric pressure, exposed to our reference pressure, P0, and a P here. So the answer will be 0, because the equation given by pressure coefficient, this one, this magnitude is 0. So you don't have magnitude, you don't have the pressure on that one. Okay. And a few dependents, as you can see in question 25. I straight will give you the answer. So there are 1, 2, 3, 4, 5, 6. They are shape dependents that will influence your drag coefficient, CD. So what can influence your drag coefficient? First one is your shape. Second one, your Reynolds number. Second one, compressibility. So this one, when you mention Mach number, Mach equal to velocity divided by the speed of sound. So in later chapter, we will look at this effect. So now we are not yet in, but as an introduction, bear in mind when you have a compressibility effect, meaning your Mach number is more than 1, then compressibility will come into place. Or sometimes not necessarily 1, sometimes it's more than 0.3, then you have the compressibility. So later we will discuss about this one in later chapter. Another one is the surface roughness with this symbol in the Moody chart. So front number, again, we introduce this one. This one is more on the open channel and wave. And composite body drag, this one, we will discuss what is this later on. So they are 1, 2, 3, 4, 5, 6. So these are the 6 factors that can influence your drag coefficient. So again, there are many things that you can discuss for your assignment already. Okay, so you can discuss about the shape, you can discuss about the Reynolds number, you can discuss about compressibility effect, you can discuss about the surface roughness, you can discuss about the front number if you're able to, and you can discuss about the composite body drag if you want to. Okay. All right, I think we stop here and then we go for a short break. All right.